Hi everyone, it's Mr. Hamilton here. This video is all about solving trigonometric equations. If you've not seen my video about the unit circle, check that out in the description below. That's going to be super important to understand how to get these possible exact solutions. If you have, then let's dig in and look at the three examples on the screen in front of you and some strategies for how to solve those. So solving trigonometric equations is really just about solving equations. It's about trying to find the value of a variable that makes an equation true. Now let's look at several strategies that are going to be helpful for us. One is we want to rearrange an equation using the reverse order of operations if possible. And that's what we would do for other equations, just rearranging to try to isolate the x as far as we can. A second strategy is simplify by isolating a trigonometric ratio, sine x, cos x, or tan x, get that by itself, and then get a number or a fraction on the other side. And the reason that's really helpful is, as you can see here, we have the diagram of the unit circle. Every coordinate on that unit circle corresponds with a special angle, and those coordinates, the x coordinate is cos of x, and the y coordinate is sine of x, and then tan of x we know is just going to be sine of x over cos of x. And so we can just look at the ratio of those two coordinates at any point if we have tan of x. A useful third strategy is to use trigonometric identities to simplify if possible. A fourth strategy would be using factoring, common factoring, trinomials, etc. if possible, and we'll do some examples with that. And finally, there's some cases where we get an angle that's 2 times x or 2 times the angle. And so what we have to do is we have to go around the unit circle twice to account for all the angles between 0 and 2 pi. Again, we'll see a situation like that and I'll describe that in more detail. So let's get to it. So the first problem says find all possible exact solutions for 2 tan x minus 2 equals 0. The helpful strategy, remember, is that to rearrange an equation using the reverse order of operations. The order of operations are BEDMAS. Some people know them as PEDMAS or other things like that, but brackets, exponents, division, multiplication, addition, subtraction. And if we're trying to rearrange an equation, what we actually do is we follow this in reverse. So SAMDEB, I call this. And so we subtract or add first, then we multiply or divide, and then we move on to exponents or brackets. And that's what we're going to do for this equation. So we're going to solve it as if we were solving 2x minus 2, but there's just a tan x where the x would be. And so now what we have is what we're going to do is we're going to do the subtracting and adding first here. And so if we add 2 to both sides, whatever you do to one side, you have to do to the other. It's going to cancel off the left side, and I'm going to get tan 2x equals 2. And now I'm going to move on to the multiplying or dividing. And so what I'm going to do is divide by 2, and by dividing by 2, I get tan x equals 1. Now there's nothing else I can do as far as rearranging that equation short of doing tan inverse of 1. But tan of x equals 1 is actually something on our special angles. And so what we should do here is we should try to find this exactly using our unit circle. And so tan of x equals 1. Well, tan of any angle is the y coordinate over the x coordinate. And so that is 1 when y is equal to x. Well, when are the x and y coordinates equal to each other? Well, they're equal to each other at an angle of pi over 4. But they're also equal to each other down here where they're both negative values at 5 pi over 4. And so the reason they're not equal here in quadrant 2 and quadrant 4 is because those are actually negative values of each other. So they're just in quadrant 1 and quadrant 3. And so our general equation is this. Because x is the angle here, don't mix it up with the coordinate x. X is the angle, is equal to pi over 4, and it's also equal to 5 pi over 4. That's what they would be equal to between 0 and 2 pi. In general, we would say this. It's pi over 4, and these two angles are diametrically opposed. That means they're exactly opposite one another, 180 degrees or pi radians between them. So we write this as pi over 4 plus k times pi. And that is our general equation where k is an integer. That's the key. If k is an integer, 0, 1, 2, 3, negative 1, negative 2, then you're always going to get it back around to one of those two angles, pi over 4 or 5 pi over 4. And that's the final answer to that first example. The second problem says find all possible exact solutions on the interval 0 to 2 pi and all possible exact solutions for 2 sine squared x minus 1 equals 0. Now, this is actually exactly what we did in the last problem, but I just wanted to spell it out so you can see that when there's different types of questions being asked. But let's take a look at this little bit difference about these brackets. If the bracket is a square bracket, it means include the 0. But the round bracket means do not include the 2 pi. And so that's important to keep in mind for this, that if you had an answer that was 2 pi, you wouldn't actually include it. And then we're going to write our all possible exact solutions, our general equation, at the end. So the helpful strategy here is to rearrange an equation using the reverse order of operations. So the first thing I want to do is I want to recognize that, writing that down, I want to get the 1 on the other side. So I'm going to add 1 to both sides. And so that's going to cancel out the left side, and I'm going to get 2 sine squared x is equal to 1. Now I'm going to divide by 2, and I get sine squared x equals 1/2. Now at this point, what I can do is I can just take the square root of both sides, because sine squared x means sine x squared. And so if I take the square root of both sides, I get sine x equals, and be careful here, it's plus or minus the square root of 1/2. Why is it plus or minus? Well, consider this. If I had y squared is equal to 4, then y could be both positive 2, because positive 2 squared would be equal to 4, or y could also be negative 2, because negative 2 squared is equal to 4 as well. And so we always take the positive and negative when we take a square root from something that was squared in an equation. Now we can take this a little bit further by taking the square root of 1, that's just 1, and then that stays as root 2 on the bottom. Now we want to rationalize the denominator generally, because we don't want a radical in the denominator. So we can multiply by root 2 over root 2. That doesn't change anything because we're multiplying by the same thing in the numerator and the denominator, and we get root 2 over 2. And so we can recognize that that's actually one of the coordinates on the unit circle. And in fact, because it's sine x, that's the y coordinate. So what that means is that the y coordinate is equal to positive or negative root 2 over 2. And so if I look at my unit circle, I'm looking for where the y coordinate on that unit circle is that. And so that would be at an angle of pi over 4. That's going to be positive root 2 over 2. It's also going to be positive root 2 over 2 when I'm at 3 pi over 4. If I go to 5 pi over 4, that's now going to be negative root 2 over 2. And if I go to 7 pi over 4, that's also going to be negative root 2 over 2. But those would all work within 0 and 2 pi. So what we're going to say here is the exact solutions on that interval are when the angle x is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So that's how we'd answer the first part of that question that asks for the exact solutions on that interval. Now the other part of the question says all possible exact solutions. And so for that, we want to write a general equation where we're going to say it's equal to pi over 4, and then all these angles are 90 degrees to each other, or pi over 2 away from each other. And so we write this as k, the integer k, times pi over 2. Where k is an integer. That's the key, is that it's an integer, so it could be positive 1, negative 1, positive 2, negative 2, 0, any of that. And it would give you one of those angles that's shown on that diagram. And so there's a solution for the second problem. Problem 3 now runs in a situation where we have an angle that's 2x. And so the question says find all possible exact solutions on the interval 0 to 2 pi and all possible exact solutions in general for sine of 2x equals 1/2. And so the strategy is to go around the circle twice to account for all angles between 0 and 2 pi, as we're about to see. There isn't really anything we can do to simplify this further. I'm just going to write this down just as it is above. But we're recognizing that sine of any angle is the y coordinate on the unit circle. And so the y coordinate on the unit circle, when is it 1/2? When is the y coordinate 1/2? Well, it's 1/2 at an angle of pi over 6. It's also 1/2 at an angle of 5 pi over 6. Pi over 6 less than pi right there. And so if we go around, we might also think that it's going to be equal to 1/2 there, but that would be negative 1/2. So we can't use anything in quadrant 3 or in quadrant 4. That wouldn't work either. And so what we end up getting is the angles pi over 6 and 5 pi over 6. But because we're trying to solve for x, that means that our angle 2x is equal to pi over 6. Well, if I try to divide both sides by 2, what I end up getting is pi over 12. That's a very small angle. You can see that angles actually become half of what 2x was because we had to divide by 2 to isolate x. And this is the reason why we have to go around twice, as we'll see. So now we look at the second angle, and that is, again, we're trying to solve the angle 2x is equal to 5 pi over 6. And so what we end up getting is, by dividing both sides by 2, we end up getting x equals 5 pi over 12. And you'll notice that those are very small angles, much less than 5 pi over 6. They've all been cut in half of what they were originally because the angle we are solving was 2x. So what we're going to do is we're going to go around now a second time. If I go all the way around the circle, but then I go up here to pi over 6 again, 2 pi plus pi over 6, well, that gives me 13 pi over 6. And so I'm going to solve that now. 2x is equal to 13 pi over 6. That means that x is equal to 13 pi over 12. And you can see that's between 0 and 2 pi. I do the same thing for 5 pi over 6, go all the way around the circle, and then go back out there again, 5 pi over 6 past 2 pi, and I get 17 pi over 6. And so 2x equals 17 pi over 6. And so that means that x is equal to 17 pi over 12. And now we have 4 solutions that are all between 0 and 2 pi. So our solutions listed would be these. X equals pi over 12, x equals 5 pi over 12, x equals 13 pi over 12, and x equals 17 pi over 12. That's the first part of the problem, but it also says give exact solutions or an exact general solution. And so one thing worth noting here is that in order to get from pi over 12 to 13 pi over 12, we've added pi. And in order to get from 5 pi over 12 to 17 pi over 12, we've added pi again. And so what we're going to do is we're going to write this as 2 different parts. So we're going to say x is equal to pi over 12 plus k, an integer, times pi, and x is equal to 5 pi over 12 plus k times pi. Now, the reason we can't write one solution for all of this, or one equation for all of this, is because going from pi over 12 to 5 pi over 12 was adding pi over 4 pi over 12, but then going from 5 pi over 12 to 13 pi over 12 was actually adding 8 pi over 12. So it's not the same thing every time that we're adding, so we have to have 2 different parts, and this is our final solution right here, so long as k is an integer. If this has been helpful, please like and subscribe. Comment below if there's any identities you're having difficulty solving that I can help you with, and check out the Proving Trigonometric Identities video right here, as well as the second part of this lesson on solving trig equations. Thanks so much for watching.